Hello world, this is Craig. Today I wanted to talk a bit about how we represent binary values. And when we represent binary values just purely for convenience, we typically use either decimal, octal, split octal, or hexadecimal. And by decimal, of course, we mean this is base 10, octal is base 8, split octal is also base 8, and hexadecimal is base 16. So let's do an example. Let's take a number like 10100011 in binary. Now we represent this as decimal, and so in decimal this is 1, 2, 4, 5, 10, 20, 40, 81, 162, 163. Oops, 163 in decimal. And of course we can also, this is that column is worth 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, so forth. We can find out what those values are, add those all up and get to the same value. But either way, we're going to find out that this value in binary is 163 in decimal. Now, as awkward as it is going from binary to decimal, it's even worse going backwards, at least for me, because long division is involved. So to go backwards from 163, we say 16 goes into 163, it goes in 10 times, that's going to be 160 with a remainder of 3. And then we have 10, 16 goes into 10 0 times with a remainder of 10. Okay, so our two values are going to be the least significant nibble is going to be 3, so 0, 0, 1, 1, and our most significant nibble is going to be 10, which is 1, 0, 1, 0. Okay, so this in binary, 1, 0, 1, 0, 0, 0, 1, 1, so that's the value that we got back from our doing our long division. Okay, so that's our binary value represented in decimal. And that's the way that, things were just typically done up all through the, the 50s and into the 60s. Well, at least the 50s, people were using mostly decimal, and it's just a pain to go back and forth. Octal makes a lot of sense. If we looked at octal, so we're going to have, that's base 8, we're going to have 8 different values, or 8 digits, and so those are represented by 0, 1, 2, 3, 4, 5, 6, 7. Or in binary, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so those are our binary values. So now we're going to talk about octal. Okay, in octal, let's look at our same value, which was 1, 0, 1, 0, 0, 0, 1, 1 in binary, which was 163 in decimal. So octal is nice because these are all numbers that we know. So to represent something in octal, all we do is we take our binary value and we break it into 3 starting from the right-hand side. So to make this more explicit, this is going to be 0, 1, 1 is that digit, 1, 0, 0 is that digit, and 1, 0 is that digit. Actually, that's going to be 0, 1, 0. Anytime that we run out on the left-hand side, we add zeros before it. And that was okay because back in the early days when mainframes had words, system words, they could have been any length. They weren't necessarily having anything to do with the byte. In fact, the byte was the system word predates the use of the byte as being 8 bits. So it was okay. Anytime that we had an octal number that didn't have enough digits in the front, you simply preloaded those with the prefix of 0. So anyway, in octal, this is going to be 3, 4, 2, and with octal we would end that with an O, or we would, I like to use a Q because I get my O's and my zeros mixed up. So this binary value, which is 163 decimal, is also 243 in octal. Now when the microprocessor came along, it pretty much defined the byte as being 8 bits and a word as being 2 bytes, a memory word or a system word as being 2 bytes or 16 bits. And if we look at the 4004, the 4040, those were both 12-bit machines. So a 12-bit address. Of course, they were 4-bit machines, but they had a 12-bit address. The 8008, that bumped up to a 14-bit address. And the 2 bytes, the 2 most significant bits in the 2-byte address were processor status. And then, of course, the 8080 and the 8085, well, that went up into a 16-bit address. Okay, so let's write another number. Let's make this one a 16-bit value. 1100100010100011 in binary. And, again, we can convert this to decimal. And so this is going to be 1, 3, 6, 12, 24, 25, 50, 100, 200, 401, 802, 1604, 1605. So we were at 1605, 0, 1, 12, 3210, and 3210 is 0, 2, 4, 6420, and 6420 is 12840. And now we're doing this one, so 12840 is 0, 8, 16, 5, 25680 plus 1 is 25681. 2, 16, and 6, or 8 and 8 is 16, 12, 13, 10, 11, 5, 13, 62 plus 1 is 5, 13, 63. Okay, so that value is 5, 13, 63 decimal. And if we were to write that as octal, that would be 3, 4, 2, 4, 4, 1. That's in octal. But the problem is that if we look at that, this number, or this digit right here, is split on a byte boundary. So here's 1 byte, there's the other byte, and this digit right here, this 2, is split on this byte boundary. And sometimes that can be a bit inconvenient. We want to store, or we want to think of something as a byte sometimes, and sometimes as a 16-bit word. Cross that byte boundary is a little bit of a problem, so that's when we use split-octal. With split-octal, we honor that byte boundary. So what we do is we write this value right here as 3, 011 is 3, 100 is 4, but then we write this as just using those 2 bits. In this case, it happens to be 2 again. But now we look at the upper one. This is going to be 0, that's going to be 1, and that's going to be 3. So in split-octal, this is going to be 310, 243, and we use the little pound sign in between these to show that this is in split-octal. Or sometimes you would still just use a Q or put a space in there. But at any rate, you got to remember that it's up to you to remember that this is split-octal. So let's look at a couple of key values. 1, 2, 3, 4. Okay, if we look at this in octal or split-octal, in octal we divide that up. That's going to be 7, 7, 7, 7, 7, 1. And so this is going to be 1, 7, 7, 7, 7, 7 in octal. But in split-octal, this is going to be 7, 7, 3. So 7, 7, 3, 7, 7, 3. Okay, so this value in, so FF, or all ones, in octal is 177, 777, and in split-octal it's 377, 377. So let's look at 0000, 0000, 1111, 1111. So in octal, this is 000, 377, and again here it's 000, 377. And now if we now add 1 to each of those, in octal, this turns into 000400, where in split octal, this turns into 001000. Okay, so this rollover, instead of 377, the next number above 377 in octal is 400, but in split octal, the next number above 377 is 001000. Okay, so that's the difference between octal and split octal. And of course, now we all know and love hex. So if we look at our value or hex, that just means that we're in hexadecimal. We've got 16 values. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And even the A, B, C, D, E, F, it took a while for that to become a standard. People wanted to use all sorts of odd things before that. But this is our attempt of writing 16 values with a single character or single digit. And of course, in binary, these are 0, 0, 0. And it's easy to break this and write this in hex. So that's a 3, that's a 1010 is A, that's 8, and that's a C. So C8A3 in hex, or we often write that as 0x C8A3, and the 0x representing that is in hex. And as I said earlier, hex actually came very late in the game, and manuals, IBM manuals in the middle 60s were still explaining hex as if it had to be explained. So it probably didn't really catch on until the late 60s, which was before my time. I wasn't playing with computers in the late 60s. So let's go look at a example of how this was used back in the day and how we were able to go between these bases. So which was the best system to use, octal, split octal, or hex? And it all came down to what you preferred, what the resident monitor required, and what assembler or compiler you were using. And you just often mixed between them. So you may be thinking in octal, but then you get Byte Magazine or some user group and you look at a program listing in that, and it may be in split octal or in hex, and so you have to just kind of adapt between those. If we look at the Altair, this is the 8800B, well, obviously they were thinking in octal because the switches are all grouped in 3s, and then here's the leftover, the extra digit at the top that would have leading 0s. But they also understood that you were going to be getting a lot of things in split octal, and so these markings up here for both the data and the address, they have marks here that guide the eye for split octal. So there's 3, and then here's 2, and then there's another mark here to guide the eye. There's 3, here's 3, and there's 2 for split octal. So these marks were to help when you're keying things in or when you're looking at things to see these in split octal. And then of course there's this big bar down here at the bottom that represented in the bytes, and so this helped you when you were doing things in hex. So this is an example of how you just go back and forth depending on and look at the different marks depending on whether you were keying things in octal or in split octal or in hex. All right, well, I think that's all I had to say about these representations of the binary values, and the reason I did this is because we're going to start talking about assembly language and learning assembler. And we're first going to do that on the 8008, and that uses split octal when we're using it in the mil mod system. And split octal is just not the most commonly used representation. So I wanted to make sure that everybody had a basis on split octal before we launched into that. Okay, well, that's it for today's video. I hope you enjoyed it. And if you have any questions, let me know. Thank you much. Bye.